Hello there, and welcome to this collection of notebooks and tutorials on advanced digital signal processing. This is a course offered by Professor Schuller at the Humboldt University of Technology. I am Renato, and this notebook is about Allpass filters. Let's get started. So far, we just paid attention to the magnitude of our frequency response, and we didn't care much about the phase. For Allpass filters, it's basically the other way around. In the beginning of filter design, we saw that we can write a transfer function with this equation here. So here we specify, or rather alter the phase, and keep the magnitude of our frequency response at the constant 1. So that means that this is equal to 1. Hence, we would like to have a filter with a transfer function h of magnitude constant 1. So the magnitude of the transfer function is equal to 1. This also means that the magnitude of our z-transform is 1 on the unit circle in the complex z-plane. We can use such an Allpass filter to implement, for example, a fractional delay d, where d is a real number, for example 0.5, which we want to delay a signal by half a sample. So in this case, we cannot simply use a memory element as in the case of integer delays. In lecture 8, we saw already that our ideal frequency response in the DTFT domain, the discrete time Fourier transform, is given by this equation here. To obtain its ideal impulse response, we can apply the inverse DTFT. We also saw this in lecture 8, but here, so what we're doing, we are applying the inverse DTFT to our ideal frequency response. So after all these mathematical manipulations here, important to remember also this exponential and trigonometry properties here, and when we replace things, we find out that the ideal impulse response is a sinc function shifted by d. So for the case of an integer delay d, this degenerates to a 1 at the dth position of our impulse response and zeros elsewhere. So we need to make this an FIR filter, and for that we will apply a window function. This is also described in the lecture multi-rate signal processing. You also find tutorials for multi-rate signal processing at Guitars AI GitHub and Guitars AI YouTube channels. So in this case here, we will use a sine window. So for this example, we will apply a sine window to the sinc function. So here is the equation for the sine window, where L is the length of the window, and then n goes from 0 to L minus 1. So what we're doing is that this avoids having sudden ends of the impulse response. We also want to keep the most significant part of our sinc function to keep the resulting error small. So what we need to do is that the samples that we will drop out, they also should be small. And to include some of the significant values of the sinc function at negative n, we will need to shift it to the positive indices. So we will shift it by n0 and to make it causal. So in this way, we will obtain the following impulse response. So it's our sinc function shifted by n0, and then we will apply a window, is a sine window, so it's a multiplication in the time domain. We can have here a Python example where we will have our window length equals to 10. We will give this shift of n0 equals to 4. So we will import numpy, we will import matplotlib to plot. We are defining our length equals to 10. We are defining our n0 here. This is 4. So here we have our window function, the sine window. So that's given by this equation here. And then we are applying the windows. We are multiplying our window times our sinc function, and this is our resulting impulse response. And this is what we're plotting. So we're plotting here the sine window. We're plotting our sinc in orange, and we are plotting the window sinc function green here in this plot. So we will use this window sync function, and we will filter test signal using this window sync function. So this is our next step here. Now we're importing SciPy to use this L filter, and we are filtering our test signal by the impulse response that we obtain here by applying a sine window to a sync function, and then we will plot here. So this is the original signal in blue, and this is the output of our filter, and we can see some errors. We can see that there is a delay, but we also see that our filter is very short. So what we can do, we can also test with a longer filter to reduce these errors. So this is what we're doing the next step. So instead of using a window length of 10, we'll use a window length of 20. So again, our sine window here, but with the new length, our sync function here, and now we need to, instead of 4, we need to give a shift of 9, and this is what we're doing here. So this is our resulting impulse response. We're multiplying our window by our sync function, and we are plotting now. So this is our test signal, and now we are shifting it by 9.5 samples. So it's just 9 from this N0, and 0.5 is the D, our delay. And now we see that we have shorter errors here. So the longer we make the filter, keeping the main lobe of the sync function in the center, the smaller the resulting error for the shifted signal X. Yeah, but we have the height of the ripples, they remain similar. Yeah. So this is what we can see. We see here just this shifted sync function by N0, and we also have the shifted windowed sync function that was the impulse response we used to filter our test signal, and we got this final result here. Now we are also interested to see the frequency response of our filter. So this now we are using FracZ from SciPy signal, and we're also using NumPy and Matplotlib. So with the FracZ here we will have our frequencies where the frequency response were computed, calculated, and here is our frequency response. So now we're plotting our frequency response. So we're using the 20 log 10, so we can see magnitude in dBs. We're also plotting the phase. So the phase will be the angle in radians, and we are using the normalized frequency. So it's from 0 to pi, and pi is our Nyquist frequency. And here's the frequency response of our filter, which is this version of the filter here with L equals 20. And we see here the phase plot also is at normalized frequency. We remember that minus d omega, so for a daily d, so the d is equal to minus the angle divided by omega, the negative slope. And we also observe the magnitude deviates from 0 dB at high frequencies at about the normalized frequency 2.8, so around here. So we are all in 0 dB, but then it deviates here. So to estimate the obtained delay for verification, we can also use this Python formula here. We will plot as a Matplotlib notebook backend here. We can also have pointers, and it will indicate with the mouse. We see that the delay is 9.46, so it's indeed roughly the desired 9.5 samples delay. Yeah. And this gives us a tool for fractional delays, yeah? But we have this attenuation at high frequencies. We will try now a different approach, so we will not use FIR filters, but we use an infinite impulse response filter, an IIR fractional delay design. So here in this paper here, this article from the IEEE, we found a way to design fractional delay IIR Allpass filters. So you can take a look here, you can download this PDF file, and in this paper here it gives us a way to implement this function. So this function will take as an argument the fractional delay, and it will return a denominator and a numerator of a transfer function. So all this here you find based on this article here, and we can test this. So we will test our fractional delay. So suppose we want a fractional delay of 5.5 samples, so we will give it this function we define here, the argument 5.5, which is the delay in samples. It will give us back, it will return a denominator and a numerator, and then we can use the SciPy signal L filter, and we will filter our test signal, and we will give the denominator and the numerator. And here we have our test signal, and then the output of the filter, which is a delay of 5.5 samples. And we can see that the extrapolated zero crossing and the delayed signal would be indeed around 5.5 samples. And we also see that compared to our previous attempt, we have now fewer ripples. So we can see the frequency response of this filter here. So we will again use SciPy signal Frac-C, and we are plotting here the frequency response. So here you can see the scale. So this is basically 0 with some rounding errors, and we obtain a nice impulse response. So there are a set of coefficients 8 mean and the frequency response. So we have here that the magnitude is practically precisely 0 dB, and this means that a gain factor of 1. And we also see the phase plot at the normalized frequency, and we can calculate if we use this here. We have 5.4, which is almost our 5.5 samples. So this is another approach. So this time we are using IIR all-pass filters. So it means that we have gain factor of 1, and we can, for example, have an application of such a filter in stereo source separation with 2 sources and 2 microphones. If we want to cancel one of the 2 sources, we can model the precise delay from one microphone to the other to be able to remove the signal by subtraction. And you'll find this application by Professor Schuller, the first time domain stereo audio source separation using fractional delay filters, and we'll use this one application of this design here. But we can also have a simpler all-pass filter that will have 1 pole and 1 zero in the Z domain for the transfer function. So this is the transfer function of an all-pass filter with 1 pole and 1 zero, where A is a complex number and A superscript with specifies the A bar specifies the conjugate complex number, and we observe here that we have a 0 at Z equals to 1 divided by A, and a pole at 0 equals to A. So the pole and the 0 are at conjugate reverse locations. So it's easier to visualize this if we have an example, and we can use Python. So here we will set A equals to 0.5, and we want to obtain pole zero plot. So here we are defining a function to plot poles and zeros. So it will display a nice plot like this. And here we will have our a and our b, the arguments of this function. So we have a is equal to a and b is equal to 1 divided by a conjugate. A is equals to 0.5, and then when we plot, we see here a pole at 0.5 and a 0 at 2. So we have a pole at 0.5 and a 0 at 1 divided by 0.5. That's 2, and this is what we have here. So this is a function. Most of the function here is doing to shift this axis and then plot this unit circle. And then we also have here we're plotting real part, imaginary part of A, real part, imaginary part of B, and where this results into this plot here. So how can we see that the magnitude of the frequency response is equal to 1? So how can we see that indeed this is an Allpass filter, that the magnitude of this transfer function is 1? So if we rewrite the frequency response, replacing z by e to the power of j omega, we will see now this 1 here before the exponential as magnitude 1. We have here that the numerator is the conjugate complex of the denominator, so the magnitude cancels to 1, and overall the entire expression has a magnitude of 1. So the magnitude of this is equal to 1. So we can see that using just one pole and one zero, we can obtain a magnitude of constant 1, and this is what we want for our Allpass filter. But more interesting now is the resulting phase, and this phase function can be found in the book of Oppenheim, the discrete time signal processing, and is given by this equation here, where r is the magnitude of A and theta is the phase angle of A. So A equals to r times e to the power of j theta. So observe that so far we assume the phase to be linearly dependent on the frequency. So for it was minus capital omega times d, and here we see to be quite non-linear with these trigonometric functions. So we can plot this resulting phase over the normalized frequency, and we can compare it with the phase of a delay of one sample, for example, where we will get this linear phase minus capital omega. And so let's do this example. If we will plot for A equals to 0.5 and A equals to minus 0.5. But to plot this resulting phase, I will use SymPy, and before plotting I will try to demonstrate that from this equation here we will get indeed the magnitude equals to 1 and the phase equals to this very complicated equation. So what I will do, I will use SymPy. So I'm importing here SymPy and the symbols conjugate. This computes the phase, this computes the magnitude, this is the complex number, this is the exponential, this computes the conjugate of a complex number, and this is a SymPy plotting function. So here I'm defining the symbols I'm going to use. Here I'm defining first this equation given here. So this is here after some SymPy manipulation. So I am just doing exactly e to the power of minus j omega So e to the power of minus j omega minus a conjugate divided by 1 minus a times e to the power of minus j omega. So this is exactly this, but SimPy has its way of already changing things. And then what I'm doing, I'm simply calling this ABS here, that will compute the magnitude of this. The magnitude is given by this complicated thing, but when we replace a by 0.5, it will give us, this is what I'm doing here, I'm replacing a by 0.5, and it gives a magnitude equals to 1. And indeed, if I replace here, instead of 0.5, if it's minus 0.5, and SimPy is taking some time to compute, but in fact it's also 1. So this is what I'm doing here. I'm replacing a by minus 0.5 from this equation here, and I am calculating the phase. So this is exactly what here. Here I'm using a equals to 0 and a equals to 0.5. So from omega going from 0 to pi, and this is the plot what we have here. So going back and recapitulating, I had this transfer function here with one pole and one zero. I wanted to see that the magnitude is equal to 1, so I define this in SimPy. Then I call this ABS, which gives us the magnitude, and it gives magnitude equals to 1. So no matter what a we replace here, we will end up with the magnitude is equals to 1. And I wanted to see this phase here. So what I do is I use this arg here. So if I apply arg to this transfer function here, and I replace a by, for example, minus 0.5, 0, and 0.5, we will get this plot here. And here we see the blue line is an all-pass phase for 0 equals to 0.5, the green line for a equals to minus 0.5, and the red line is for a equals to 0. And the phase is a pure one sample delay, z minus 1, for when a equals to 0. So here we can be seeing that the beginning and the end of the curves are identical at frequency 0 and at frequency pi, but only in between the all-pass phase deviates from the one sample delay. So for a equals to 0, the all-pass becomes identical to z to the power of minus 1, which is a delay of one sample. So this is a pure one sample delay, and here we can see that it behaves very similar to a delay, but we have, for different values of a, we have different characteristics. And such an IIR all-pass can also be used to implement fractional delays. So in the above plot, we observe that we have different slopes or different derivatives of the phase function with respect to frequency, which shows different group delay for different values of a. So for instance, if we take the green curve, this green curve is a is equal to minus 0.5. At the frequencies below half the Nyquist frequency, it has a slope which is about a third of the slope of the red curve, which is the delay of one sample, and it represents a fractional delay. So this is a equals to 0. This is a pure one sample delay, but for example here we have different, this is our normalized frequencies, and this is our phase. So this application is described in more detail, this splitting the unit delay article, the IEEE signal processing magazine, and you can download here and take a look to see how it's done. We can also reproduce the plot from the previous session by using this formula here, this function. We're defining a warping phase function. It takes as an argument an input vector of normalized frequencies and all-pass coefficients, and will return this warping phase. So here we see this is the same equation that we found in the Oppenheim book, Discrete Time Signal Processing. So we see that for A equals to 0.5, that's the blue curve, we observe a stretching of the low frequency range, where a small part of the low frequencies stretch over a wider phase range than the other curves. So when we take a look here again at this plot, here we see the blue curve here, that's the curve from A equals to 0.5, and we note there is a stretching of the low frequency range. So where the low frequency range is here, and we see stretching of the low frequency range, where a small part of the low frequency stretch over a wider phase range than the other curves. So when we compare with the other curves, we see this stretching. Yeah. So this is another way to have the same plot. That time we used SymPy to obtain this plot. So we didn't use the equation given by this book. We went from this equation, we calculated the magnitude, we calculated this phase using these formulas here using SymPy, and we had this plot. At this time we are defining this warping phase when we are defining this equation of the phase here, and we are having the same plot. Yeah? The phase at the output of our phase function can be also interpreted as a normalized frequency. This means its output can be the input of another warping phase function. So an interesting observation is that the warping phase function with coefficients minus compass conjugate A is the inverse of the warping phase function with the coefficient A. So how can we observe that the warping phase function with the coefficient minus conjugate A is the inverse of the warping phase function with coefficients A? We can use Python. So here, this is the Python code. Here importing matplotlib to plot. So here we define a range of frequencies from 0 to pi in steps of 0.01. So here is A is equal to 0.5 times 1 plus j, and then we are having here, we are calling our warping phase of the warping phase with omega na and the minus a conjugate. So if we remember, the warping phase takes frequencies, an input vector of normalized frequencies, and the all-pass coefficients. So all-pass coefficients now is the minus a conjugate, and the frequencies is the warping phase of A. Then we have here, we see that indeed this is the identity function, and this shows that interpreting the all-pass as a normalized frequency warper, the all-pass with coefficients A is inverse to the all-pass with minus conjugate A. Again, we can use the FracZ from SciPy signal to compute the frequency response of this example all-pass filter. In this case, A is equal to 0.5. Here it was this the transfer function for this filter, and we are defining our coefficient vectors. So this example A is 0.5, then we will have the B is minus A conjugate and 1, and A is 1 and minus A. And what we expect from this is to see the magnitude to be constant 1, and the phase angle to be like what we saw from the phase formula from the book of Oppenheim and Scheffer equation. So here we are defining our vectors, we are importing our libraries, and we are calling the frac and we have here the plot of frequency response. So we can see there is this scaling here. So this is actually a 0 dB, which corresponds to unit gain. So this is a constant 1, the 0. And we have here the nonlinear phase, as we saw in the phase plots before. We can also obtain the impulse response using the L filter from SciPy. So we're defining our impulse. There's a 1 at sample equals to 0. The rest will be zeros. We are filtering this impulse with the numerator and denominator we defined here. And we have our impulse response for our IIR all-pass with A equals to 0.5. And here is very interesting to notice that we have the first non-delay sample not at 0 but at minus 0.5. Yeah. So we can also print the first 4 elements of our impulse response. We have here, so the second element corresponds to the delay of sample of one sample. So this is the z to the power of minus 1, and it has a factor of 0.75. Yeah. And then there are more samples going back into the past, exponentially decaying. So this means not only the past samples goes into our filtering calculation, but also more past samples, and even the non-delayed sample with a factor of minus 0.5. So this is actually a problem for the so-called frequency warping that we will see in more detail in the next section. And if we want to use frequency warping in IIR filters, because here we would get delayless loops, and they are very difficult to implement. So with FIR filters, this is not a problem though. So these properties of the all-pass can now be used to warp the frequency scale of a filter by effectively replacing e to the power of j capital omega to e to the power of j, a function of capital omega, in our frequency response. So for instance, we can map it according to the so-called Park scale that is widely used in psychoacoustics. So a common approximation of the Park scale is given by this equation here. We have these arctons here, numbers. So this f is the frequency in hertz. So the Park scale can be seen as an approximation of the change in frequency resolution over frequency of the inner ear filters of the human ear's cochlea. So because of the structure of our cochlea, the ear has different sensitivities for different frequencies and different signals. So the signal dependent threshold of audibility of the ear is called the masking threshold. It has more spectral detail at lower than at higher frequencies according to the Park scale. So we can plot this Park formula in Python. So here we are defining some linear space from 0 to 20,000 in steps of 1,000, and we are computing this Zwickers Park approximation formula. So we're defining this formula here in Python, and then we're plotting Park over hertz. So here we have the frequency in hertz, and here we have the equivalent of frequencies in Park. So here we can see that the 1 Park at lower frequency has much more lower bandwidth than at higher frequencies. If we take 1 Park in the lower frequencies, the bandwidth is much higher than if we take 1 Park the higher frequency. So this means the ear can be seen as having a higher frequency resolution at lower frequencies than at higher frequencies. So imagine we want to design a filter or a system for hearing purposes, for instance, and we would like to model the masking threshold of the ear for any given signal by some linear filter, FIR or IIR. So then it would be useful to give this filter a higher frequency resolution at lower frequencies, such that it matches the smaller details of the masking threshold at the lower frequencies. The thing is that if we look at the usual design methods, they distribute the filter details independent of the frequency range. So for instance, what we saw with the Remes method, where we have equally distributed ripples. Here we can now use frequency warping such that we enlarge the lower frequency range and we shrink the high frequency range accordingly, such that our filter now works on the warped frequency and sees the lower frequencies more detailed. The lower frequencies are more spread out in comparison to the higher frequencies. So how do we do this? For some frequency response define, we would like to warp the frequency omega with some function of omega according to our desired frequency scale, such that we get the frequency response that as a function, the phase is a function of some capital omega. And this is exactly the principle of an Allpass filter, which has the frequency response given by a function of capital omega. Usually we would like to map positive frequencies to again positive frequencies, but we saw that the function of the frequency capital omega in the phase of Allpass becomes negative. So we need to take the approach to replace z in the argument of our transfer function with the reverse of our Allpass transfer function. So this is replacing all delays of our filter to be warped by our Allpass filter. In this way, we replace our linear function on the unit circle in z with the nonlinear warped function on the unit circle h of Allpass. Hence, we get the warped transfer function like this. And the resulting frequency response becomes this h warped, where we have here the phase as a function Allpass of capital omega. So here we can all see that we obtain the desired frequency warping. So what does this mean for the filter implementation? Yeah? We know that our FIR filters always consist of many delay elements, z to the power of -1. So let's take a look at an example. If we take an FIR filter, we have here the frequency response, and its warped version is then here we're replacing with this Allpass frequency response here. And to obtain a desired filter, we now first have to warp our desired filter and then design our filter in the warp domain. Okay? And observe that the warping turns an FIR filter into an IIR filter. Okay? An example of this kind of design can be seen here, and here we have a 12 order filter approximated here. So we have the desired here. This is a 12 order approximation. Here is the same desired, but a 12 order approximation with warping approach to the Bark scale. And you can see there are more information about this in these two papers. One is the Bark and the ERB bilinear transforms, Julius and Jonathan Smith and Jonathan Abel, and also with Schuler, Kramer, and Wapnick, and Hirschfeld, frequency warping in low delay audio encoding, the IEEE International Conference on Acoustics, Speech, and Signal Processing.